Hello everyone. Let's solve the laboratory exam 1. Now, in this exam, the task was to write the code for the p-design function here. The input arguments were the numerator and denominator of the open loop transfer function, and the third argument was the settling time for the closed loop. So the function also should return a k, which is the p-type controller itself, and a flag that helps us to determine if the solution is valid or something else, if it's not valid. So now in order to be able to code this function, we need also an additional script here. And let me start MATLAB, by the way. We need an additional script here where we try our function out. Now, let's start with the test function here. Now, let's define, for example, a symbolic system here. Let's have S. Now, in order to be able to solve this, we did disregard the zeros of the transfer function. So ns is basically a coefficient in our case. It could be a more general solution, but that was not necessary because the point of this lab exam is to be able to solve it in a certain time limit. And also note that we've just started the course, so to be able to solve this, we did restrict it to coefficient. So now let's have, for example, the coefficient 2. This could also be equal to 1, but let's generalize the solution here. And we will also have ds, which is the denominator. And by the way, there is also another limitation. It's the third order transfer functions that we're trying to address here. So therefore, we have s cubed plus, let's say, 2 times s plus 1, or s squared, plus s plus 1. So we have to define the symbolic expressions here, and we also need to define the settling time because these are the arguments of the function. So if we call the function, we will basically use this definition here. So let's have that. So the definition was also how we invoke the function. We have the function name, the argument list, and also the return list. Because it will return multiple outputs, we have an array notation here. So, and then we should also look for the controller coefficient and the flag. So in this function, what we have to do is we have to do the following. We have to design a p-type controller. We have the numerator and denominator. So the simplest way is to use the algebraic method, namely the polynomial coefficient method, in order to synthesize this controller. So, therefore, first of all, we don't know what the coefficient is going to be. So let me also change this to k-val for now. So we will have a real k-value. We will also have a closed loop. So let's find that. So we have basically, what you can do is you can use also this here. You can generate the open loop, like ns divided by ds. And then, since you have k, you can go ahead and use the relation here, k times gss, and then divided by 1 plus k times gss. And then you can also use num then in order to get the numerator and denominator. So let's say num then is equal to num then of tss. And then we will have the denominator. So of course, when you're writing code like this, it is also not really that easy to debug it. So if I run test, for example, here, we didn't assign the value. So one of the errors is to assign the output variables here. So for now, let's say k-val is equal to 1 and the flag is equal to 0. So once that's out of the way, you can see now we can run the test script here. And if we again don't use the semicolon, we can also see the intermediate outputs here. So we have such a closed loop characteristic polynomial. Now, since this is a third-order system, and since we have only the settling time, we have to also construct another polynomial that should be the desired polynomial, which should include our desired pole locations. So we have to add s plus p, so therefore we need a symbolic p. And then we also need the second order part, 2 times zeta times omega n times s, and then plus omega n squared. So therefore we also need omega n. And since we have a settling time, we can use the settling time formula, zeta times omega n. And of course, we have the numerical value of ts, and we try to come up with zeta and omega n values. So therefore, we use the inverse formula here that would correspond to settling time times omega n. And this would give me zeta. So, of course, this is not directly the value of zeta, but it is basically the relation between zeta and omega n. And if you remember, previously I've talked about that, if we have a certain settling time, we actually know the zeta times omega n multiplication. And if you think about it, I'm directly plugging in here 4 divided by ts. But to be general, I'm using zeta equals 4 divided by ts times omega n. So, now at this point, it is crucial to define this omega n real. Because in the task here, what we have to account for is that if the solution is okay, which means that I have a k value and I have a stable closed loop, then I'm good to go. I can use that k. I have to return 0 as the flag. But if it's not on the root locus, if I cannot achieve such a design, then I need to warn the user here. So therefore, we need to return 1. And exactly this case will be determined by defining omega n real. Because if it's not on the root locus, then by definition, omega n should be real and positive. That will be violated. Because the sum of some parameters plus omega n squared will be equal to a negative value. And we've seen that in the laboratory in, I guess, week 2. I'm not really sure. So if this is violated, if it's not on the root locus, it will be. The square of omega n should be negative, therefore it should be complex. So if you can also try to detect if it's complex or not, but the simplest way would be to define it real. And since we will use the coefficient equating method here, so let's define our problem. Our problem is to use coefs of PCS, or den in our case, s, all. So you can also see that I need sims s here, because I didn't define it here. So be aware that the functions have inside them their own scope, their own memory space. So they don't share the variables with this main script, for example. You can do that. You can work around this using the global keyword, etc. But I'm not going to go into detail. But this has its own namespace, the workspace. So therefore, if you are defining x in here, you can also define x in here, because this is a local scope. So for that reason, we have to define the symbolic s variable here. Of course, it could be more adaptive. We could determine based on ns and ds what the actual symbolic variable is, but I'm not going to need that, because the actual thing is the algorithm. So we don't have to think about everything in this case, because we're not producing an industrial application. It's just a lab exam. So we can define some things on our own, and the symbolic s is one of them, because we used s for all the time. So therefore, it's okay to use s and k here. So based on this, I need to form the problem here. But I did something here. I did define ns equals 2. And it could also be the case that the s cube coefficient here is something different than 1. So in that case, what will happen is the following will happen. We'll see it in a moment. So I need the coefficients of PDS. Of course, I did write it down like PDS, but PDS is basically the second order part, and then we have PES and the multiplication here. So you can use whatever you want, but I'm using this for now. So if I try to define a problem like this and run test here, you can see that in the first equation, there's a false statement. And the reason for that is that x cubed had a different coefficient than 1. So the best solution is to just divide the whole equation, the whole polynomial, into the first coefficient here. So I can do that by determining the coefficients of this. Let's say this is PCS. Let's get the coefficients of the denominator. There we go. And let's normalize it or divide it into its first coefficient, the highest order term. So once I've done that, and once I change this to PCS, there we go. Now it's 1 equals 1, but there's the effect of dividing by 2. We can see that. So now at this point, I will be able to hopefully solve the problem. So let's store this in this solve variable here, and let's see if we have a solution or what the solution is. So we can see that we have basically two solutions in this case, and I'm assuming that omega n squared was in the equations, therefore there should be a symmetric version of omega n. So we can get rid of it by using basically the following definitions here. We can say sol dot omega n is equal to this, and we can also convert it into double variables because we don't need anything symbolic now. So we have k-val and then p-val. Of course, sol.p should give us p-val and sol.k. Now, we have to have p positive if we want to have stable solutions, and we have to choose the positive omega n values. So therefore, let's start with index equals omega n val positive, because we're interested in positive omega n values, because we have multiple omega n values, therefore multiple solutions, 2 in this case. So we have to eliminate some of them. So we have that. And then also p-val and k-val should be eliminated accordingly. So let's see what our solution looks like. There we go. Now we can see that the omega n value is 7.77, minus 454, and minus 7.5. Of course, in this case, we can see that the p-val is negative, which means that this should be unstable. Now, let's also change our example here. Let's change the whole system. Now, let's, for example, include the following. Let's have s times s plus 5 times s plus 8. Now, and of course, let's change this to 1, because it's not really that important. Now, if we have settling time 10, for example, and if we try to use the solution here. Now, for this case, we have positive p-val, which tells us that we have basically a stable solution, and we have omega n val positive, and we have just a unique solution, and k-val is this. So in this case, what we can do is we can determine if the solution is the one we are looking for. Now, let's check if p-val is positive. Now, in this case, if it's positive, we can safely return the controller coefficient k-val here. We don't need k anymore at this point, so we can substitute it back into k. So k should be equal to k-val, and then the error flag here should be equal to 0. So the first case corresponds to basically this one here. So let's try it out. Now we can see that we have k, so we can also delete this and delete the semicolon here and use it like this. So we can see that k is a certain value and 0 is the flag. So now what about the solution where we cannot assign the settling time, or where the point of interest is not on the root locus? So let's try the settling time 1.5. So as you can see, there's an output argument problem. We didn't assign them, which means that it's first of all not stable, or at least not at this point. So what we can do is we can now check what sol looks like. Now you can see that the solution is not found. The reason for that is the definition omega n real, line 12. So this is the crucial part. If you did this like omega n real, and if you check for the size or dimensions of the solution, then you can determine if it's on the root locus or not. So, but we cannot use sol itself directly because it's a struct, so we need to access one of the fields. So what we can do is we can basically try to access k and check if it's empty, or if the length, or if the size, so if length equals 0, basically. So let's check that. So we can see the statement is true, so therefore we can check it and look for it. Now, if this is 0, we will return something, and else, if it's not 0, then we will again calculate omega n val and k val. If it's 0, we don't have to narrow down the solution because there's no solution at all. So in this case, what we can do is we can just return an empty k value here, an empty array, and the error code should be equal to 1. Let's check it again. Yep, not on the root locus. So now, if we test this, we can see that this point is not achievable here. Now, what about unstable solutions? Let's change the settling time here, and let's try to run this. Again, we have a non-assigned output here, which means that probably we are in this case. It makes also sense because it could be equal to 0, marginal stability. Let's take it also as unstable solution. So p-val should be negative or 0. So in that case, we can again use the same thing here. So we don't have any k, but our flag should be equal to 2 because this is an unstable solution. You can also return what k looks like. It depends on you. So we can also return that. So let's test it again, and again, and again. Didn't we assign k-val? Interesting. So let's see what k-val looks like. Oh, I guess. Oh, I should add it here. So k-val is equal to 0. It's because of the settling time here. But here, due to omega n, let's say omega n, omega n is equal to 0. That's understandable. So yeah, because omega n does not satisfy this, we've eliminated it. Therefore, we couldn't access any k-val here. So let's stick with the empty solution here. If you want to do that, you may check this before using this. But there's also the important point that this should be basically just one element. So if you have multiple elements in p-val, for example, let's say -1 and 2, then you have to check individually. So in order to prevent that, we can basically eliminate them based on omega n val. But since we are trying to match the settling time here, or we're trying to design a controller for the settling time, that's not really a concern that we should look for. Because again, we're not trying to professionally code something that will be used in real life. It's just a lab exam. So the important thing is to know that if we have omega n squared negative, that means that using the algebraic method, we are not able to calculate or solve this problem, which is given in line 15. Attacking this from the root locus is not really that easy via code. The best approach here is to use the algebraic method here, which we have used here. So it becomes really easy to solve here. So the test cases, of course, are not really that easy to think of, but in the laboratory, if I'm not wrong, we've used this here, and there was this 1.5 settling time example, and we've also seen that it's not possible to achieve this design because it was not on the root locus. Of course, lowering this would at some point also end up in maybe unstable solutions. So therefore, it's important to check this. So check the test cases here. That was basically also the part that you should have come up with. So now in this case, we can see it is possible to assign settling time 10. So let me maximize this here. So if I run test, we can see that for the first case, settling time is equal to 10. This is the controller, and this is the flag. If we have 1.5, it corresponds to case 1, and if we have ks equals 1, this corresponds to the error flag 2. Now, it was also important to submit a function that runs, and that's also really important. When you call the function with certain variables, it should at least run. So be careful next time for that. Before you submit, test your function and then submit it. And also, again, if you use some inputs and you have, for example, multiple values, multiple solutions in this, you should also check that. So you can do that by checking for the length of one of these variables here, for example, omega n val. And if you're not sure, what you can do is you can just cycle through them using this here and manipulate them or check if they're valid or not. Now, in our case, this should not happen, of course, because it's settling time. It's not really possible to end up with those kind of solutions because it's a third order system. We didn't check for if it's if the arguments are valid. Again, it's not really that important. We assume that they are valid. So that's basically it. Now, to conclude this video here, we did look at the... Oh, I did, by the way, give the system for equals 10 here, and we've also seen that this works basically. Now, changing the settling time was basically sufficient here in this case. So that's basically it. So see you next time.